Alrighty, so the first thing I'm going to do is move on over to OneNote, where I'm going to answer this question. All right, so right now you guys should all be seeing OneNote. Perfect. All right, so Rene is playing with a large spherical rock at the edge of a cliff. The rock has a mass, a radius, and it's rotating at a certain speed. What is the total energy of the rock? All right, so let's think about energy. Well, we know that the total energy, which we'll call T for now, is equal to the sum of the kinetic energy plus the potential energy. And potential energy is something that we get to arbitrarily set. Well, not arbitrarily, there's some strategy. So this is the cliff. Let's draw that as the cliff, and here's the rock. If we set, well, so potential energy, as we know, is equal to the mass of the rock times the gravity times its height. Relative to some point. So if we can set that point right here at the bottom of the cliff, then H is going to be equal to 0. So there will be no potential energy. So that term goes away. All right. So now, with that in mind, let's talk about the kinetic energy. And just as a point of note, the reason I did that is because we are trying to calculate the total energy of the rock when it reaches the bottom of the cliff. So I want to calculate the energy at the bottom of the cliff and making the potential energy at that point 0. So, perfect. All right. So now what's left? Well, we have two types of energy. One is going to be the kinetic energy and one is the translational energy. Sorry, let me repeat that. Total energy is equal to the total kinetic energy. So what is the kinetic energy? Well, there's two forms of kinetic energy. One is the translational kinetic energy, the energy that the rock has by virtue of moving up and down, and the other one is the rotational kinetic energy, the movement energy due to the rock, that just the fact that the rock is rotating. And there's two different ways to calculate it, or they each have their own formulas for calculating this rotation. So let's start with the translational energy. So K translational, we might remember that formula as, let's see. There we go. Now let's do it here. K translational is equal to 1/2 mv squared. Assuming that the initial velocity is 0, then we're confident saying that. All right, so we have the mass, where m is the mass and v is the final velocity. We know the mass of the rock is 215 kilograms, but what we don't have is its final velocity. So that's something we actually need to calculate. Luckily, we do have some formulas that we can use to calculate that too. We know that the total distance that travels the rock, in this case, since it's following a vertical distance, we're going to call that distance delta y. So we know that delta y, and I'm going to do this in blue. Delta y is equal to the initial velocity in the y direction times time plus 1/2 a delta t squared. This is one formula that you can absolutely use, but I'm actually not going to use this formula because we don't have time and we shouldn't need to solve for it. There's another formula we can use that looks like this. Vf squared is equal to vi squared plus 2a delta x, or delta y in this case, since it's following the y direction. This is a much better formula to use since we know the acceleration. This acceleration is due to gravity, and we know the total distance it follows. And we know the initial velocity is 0. The rock starts off with an initial velocity of 0. So we can solve for Vf squared, which is actually even nicer because that's actually the term we're looking for, Vf squared. So we can say confidently that K trans, actually let's switch back to red now that we know this formula. K trans is equal to 1/2 times the mass times 2 times the acceleration of the rock, which is gravity, times the total distance it follows, which is a number that is given. All right, so that's one form of energy. Now let's move over to the rotational energy, which I'll do. So just very similar to the translational kinetic energy, K rotational is equal to 1/2, but instead of the mass, we use the corresponding rotational term, which is called the moment of inertia. times its rotational velocity, omega squared. So what is the, first off, what is the omega? What is the rotational speed? That is a number that is provided for us. It is rotating at 3.2 radians per second. Awesome. And so what is the moment of inertia? Well, that is a number that differs based off of the shape of the object we are talking about. A quick Google search, which I will show you here, for the moment of inertia of a sphere gives us the formula of 2/5 mr squared for a solid sphere rotating about its center, which is what we're dealing with. So going back over here, knowing that our moment of inertia is 2/5 mr squared, I can fill that in. K rotational is equal to 1/2 times 2/5 mr squared omega squared. All right, and we know the mass and we know the radius, so those numbers are provided for us with over here in the mass. So put it all together. Since we know that the total energy is equal to the translational kinetic energy plus the rotational kinetic energy, we can say that the total energy, so let's go back to green, that the total energy is equal to 1/2 m times 2a delta y plus 1/2 times 2/5 mr squared omega squared. And all that's left is to plug in the numbers, since we know that this is going to be gravity, this is going to be the height of the cliff, this is going to be the mass, this is also the mass, we have the radius, and we have the rotational velocity. And I will let you do that calculation on your own. Best of luck.